and today I'm going to talk about dark energy. The gist of it is, or like the basic rundown is like 2/3 of the universe is currently estimated to be dark energy, rather than you might have heard the term dark matter as well before, and it's basically responsible for the universe constantly expanding. And it's currently like the largest question in all of cosmology that's currently still unanswered. And I'm going to walk you a little bit through the history of this and what it really is and what you can do, or what's interesting to know about it. So, in the 1920s, scientists found that the galaxies were actually drifting apart. So, 1929, a guy named Hubble, you might have heard of the Hubble Space Telescope, the Hubble scientist, he found in his observations that the galaxies in our universe, they're actually drifting apart. And if you, like a decade earlier, Einstein in his general theory of relativity, he had kind of predicted that the universe is dynamic and not constant. Because what people were thinking is that, like, if you think about the universe, everything is kind of in its place and everything is kind of where it is. And galaxies are someplace, and the distance between them is somewhat fixed. And just, for example, from here to the Andromeda galaxy, like the distance is kind of fixed. And the universe is kind of this constant thing that is there. But Einstein, already in the general theory of relativity, kind of predicted that the universe was dynamic and not constant. And he put in an equation, but when he came up with a general theory of relativity, what he was predicting, because mass attracts mass, you might know this from school, like two big masses attract each other, like the moon and the Earth, or the Earth and the sun. And so basically what you're expecting from those equations, also already from Newton's equation of motion, just like the super basic mechanics, that the universe is kind of collapsing, right? Because masses attract each other, you would expect, if there's a lot of mass in the universe, it attract each other, and basically over a long time it just all comes together and falls together in the same place. But since people were thinking it was like keeping in the same place, Einstein put in a constant into his equation that made the whole thing stay in its place. He just added a constant, like a constant force, to his equation that made everything stay in place. And after he found out that the universe was actually expanding, he called it the biggest eselei of his life. And eselei is like it's a folly. It's the dumbest thing he basically he's ever thought of, was this constant that kept the universe where it is. All right, so this is and then in the 1930s, they realized that the stars in galaxies, they move way faster than predicted via Newton and Einstein's equation as well. So basically, we have everything's drifting fast apart, and everything is going faster than we thought with Newton and Einstein's equation. So we need something else in order to make this whole stuff work. And in the 1970s, people come up with dark matter. Dark matter, you might have heard about before, is something like you can't see it, but it has gravity. And the way that we know that this stuff exists is we can observe it, because you can't see it with the telescope. But if you have let's say you have like a sun here, or like anything that's emitting light, and you're here, and there's like dark matter in the middle. You won't see the light come like this, but you will see the light bend around the dark matter in a curved line, right? It'll be like a curve. Let me actually get a paint ready here. So yeah. So basically, we know dark matter exists, and it's currently estimated as like 5 to 6 times the visible matter. So everything that you can see is like only 5 to 6 times. Everything you see 5 to 6 times that, you actually have dark matter, which is like matter that is there, exhibits physical properties that you can be observed with like measurements, but they're not there. All right. So that's dark matter, but that's not quite yet dark energy. Which brings us to 1998. And in 1998, they were observing supernovas, and they were measuring what has happening to supernovas, because supernovas are like when you see them explode, you basically can look back in time because they're so big and they've spread so far across the universe. You can and the supernovas that have exploded such long times ago that when you see them in the telescope, they've like exploded millions and billions of years ago. So basically, you can look back in time, kind of like an archaeologist unearthed things. You were observing these supernovas, looking back in the universe and trying to understand how the universe has changed back in time from these billions of years ago. And what you found was, well, we already knew from the 1920s from Hubble that the cosmos was expanding. But if you're thinking of something like a spring, like a motion, you expect it to slow down with time, right? So you're expecting the universe to expand, and it goes like really fast at the start, and then goes slow and slow and slow until a point where the gravity becomes larger, and then you pull back together. But what they found is when they observed these supernovas, because they could see how fast the universe was expanding billions of years ago, and they can measure how fast the universe is expanding now, that actually what they expected is the slowdown, right? The slower expansion with time. But they found out that it expands faster and faster and faster and faster. The universe is expanding faster and faster with time, which is really weird, and they thought they made a mistake in their calculations. But they published this stuff in the end. And in 2011, they actually got the Nobel Prize in Physics for it, for observing that the universe was expanding quicker and quicker and quicker. So no one knows really what dark matter is, and what dark energy is. But you're saying dark energy is something that accelerates the expansion of the universe. So there must be a bunch of dark energy out there. There's an energy which we don't really know what it is. And it makes the universe expand faster and faster. And you have no idea what physics lie behind it and what equations lie behind it. It's basically the biggest riddle in all of cosmology. And then the funny part is Einstein said his weird constant was like the dumbest thing he's ever said. But these days, scientists actually use the constant, but they don't use it to keep the universe constant. But they use this constant to make the universe go expand even faster and faster and faster, to account for this what is called dark energy. It's called lambda cold dark matter. So the lambda for the dark energy and dark matter for the dark matter, right? So the funny thing about, and this is just at the end, dark energy is a lot smaller than you would kind of expect it mathematically to be. So current scientific models for the dark energy don't really add up. People just kind of build around with their models, and it kind of explains the expansion of the universe with a constant, but you don't really know what it is, and it's kind of not as large as people thought it was. So there's some theories, like inflation theory, is saying that the universe expanded really quickly to the size of the Earth from a tiny dot, and then slowed down and does it as a constant rate. But all of these things are just models, and everything's the big question mark, because it could just be a wrong model. And to give you an idea of why this could just be a wrong model, is in the end of the 19th century, people couldn't explain light bending around objects, right? Or light bending and stuff like that. So people were saying there's this ether. And the ether is a little bit it's super flexible, but at the same time it's rigid like steel. And they just made up this model it was called the ether. And the ether was basically responsible for explaining everything that physicists couldn't explain. It never really made sense back then, but it's just a model that you used to explain why stuff wasn't the way that you thought it was behaving. And then Einstein came along with the general theory of relativity, and his theory kind of plausibly, explained what it was, and you didn't need the ether anymore to say oh yeah, there's this kind of object that kind of feels like elastic and then sometimes like steel. And another good example is like before people found out what oxygen was, they thought there was something called phlogiston. Phlogiston was in the air, and when you burn something, the phlogiston from the air came and reacted, and the phlogiston magically made things heavier, because you feel like if you take magnesium and you burn it and then you weigh it, it's heavier before than it was afterwards, because the magnesium reacts with the oxygen in the air. So people were like, oh, there's this magic phlogiston, and the phlogiston comes while something's burning, and then you get, something heavier. It's still the same. But we found out it was oxygen, and there's no such thing as phlogiston. It's basically evaporated into thin air. Word joke, haha. But the same way, dark energy might just, like, the way that people think of dark energy right now might also be complete garbage. The same way that phlogiston was garbage, the same way that the ether was garbage. In terms of, like, it's just a way that we currently explain something that we have no clue how it works yet, until some really smart mind like Einstein comes along and solves this dark energy problem for us, or for cosmologists. But yeah, dark energy is the force that drifts the universe apart. Nobody knows what it is. It doesn't really behave the way that is mathematically expected. And if you have an idea what dark energy is, there's your next Nobel Prize in Physics right there for you.